Okay, and for the final talk of the day, of the session, Anders will tell us about how to reason about weak isolation levels using Iris.
Yeah, so hello everyone. So I'm here to present our paper, which is really about how you can verify transactional databases. So the databases that we consider, they're quite simple. They're key value stores, and they just have these two operations. So you can either read from a key, or you can write some value into your key. So you can write 1 into X. Now, databases, they run in very highly concurrent settings. So there could be thousands or tens of thousands of users wanting to access this database at the same time. And as we all know, then users of databases, they're very impatient people, so they don't like to wait around. And if they wait around too much, they become angry, and they become all red, as you see. So it's very important that our database is fast, that it has very high throughput. But at the same time, we must, of course, maintain the correctness guarantees of the database, so the guarantees that we are going to provide the users. Otherwise, everyone is just unsatisfied. So if we are in the business of implementing databases, we really have to balance these two things. So as much throughput as possible, and at the same time, it should be correct what we're doing. So most major databases, if not all databases, they provide transactions. And transactions, they are very hard to get right. And at the same time, they're really something which can slow you down and give you very low throughput. So this is what we focus on in this paper. Now, what is a transaction? Well, it's sort of a way to group individual database operations into these units that we can then reason about. So for clients to be able to group their operations into these units, we have to give them 2 additional operations. So now they also have a start operation and a commit operation. So as you see, to start a transaction, a client is going to say start, and then they can do as many reads and writes as they want. And then in the very end, when they are done, they can use the commit operation and commit all of their changes. Now, what transactions gives us, and the reason why we want them, is that instead of having guarantees for the individual operations, we can now have these guarantees at this unit, this grouping level. So we can talk about guarantees for transactions. And sometimes it can be the case that a transaction is just about to violate some guarantee of the database. So therefore, the database needs the ability to reject some transactions. So in practice, this means that the commit operation, it can actually fail. So it can be the case, a client is about to commit some transaction, and the database sees that this is not okay, so I'm going to fail you and tell you to try again later on, and then roll back your changes. Now, what are then some of the reasons why sometimes we have to fail these transactions? So that's because we are about to violate these guarantees. And there are some things we can always count on when using transactions. So there are 2 things which are like baseline guarantees. And these are that rights, they're applied atomically. So either no rights are applied, or all the rights of the transaction is applied. Then we also have this property that the transaction, it runs sequentially internally. Now, what does that mean? So it means you're reading your own rights. So for this transaction, when you're writing 1 to X, and you're just reading X thereafter, you always know that this is going to return 1. You see your own changes. So the things that I haven't told you about yet is what about all these non-local reads? What about the reads that you're doing from all the other potentially concurrent transactions? What are you actually allowed to see? And to talk about these, we have a bunch of isolation levels. So they state how isolated is your transaction from all of the other transactions. What can you actually see? So we can use these isolation levels to answer questions such as, can I execute my transaction as if I'm the only one in the world using this database? And it turns out that the answer to this question is actually sometimes yes. Sometimes you can imagine that you're the only one. So one of these isolation levels, often what we consider the strongest one, is called serializability. So under serializability, transactions, they execute one at a time. So in this example execution on the slide, these boxes are our transactions. So first we apply the rights of transaction 0, then we apply the rights of transaction 1 on top, and on top of that we apply transaction 2 and so on. Now, underneath this transaction, we have these arrows. So I call these read arrows. So it means, for instance, that transaction 1 is reading from transaction 0, and transaction 2 is reading from this snapshot created by first applying transaction 0 and then transaction 1. And what we get from serializability is that these read arrows, they're always perfectly aligned. So each transaction always sees the most recent snapshot. Now, the problem with this strong guarantee, and I was mentioning throughput before, it is that this can imply a lot of failed transactions. So all concurrent transactions, they are competing for being the next transaction in this line to be applied. So in the worst case, it can be that we have to fail one, but the winning transaction of all our concurrent transactions. So this will really tank the throughput of our database. So we are quite lucky in that there are weaker guarantees, and we call these weak isolation levels. So many people have made the observation that not all use cases need strong isolation. In fact, if you create an application tomorrow and then you need a database and you find this database on your favorite cloud provider, then as default, it is not going to run strong isolation. It will run one of these weaker levels. And an example of one of the most popular levels is called snapshot isolation. So this is different from serializability in the sense that transactions, they read from snapshots of the database, and we call these starting snapshots. So they're the most recent snapshot at start time. Then at commit time, a transaction is allowed to commit only if it has no write conflict with any of the other concurrent transactions. So I have an example execution again. The first two transactions, 0 and 1, they're just like in serializability. The read arrow for transaction 1 is perfectly aligned. But then we have two concurrent transactions, transaction 2 and 3, and they share the same starting snapshot. Yet we allow them to commit because they don't touch any of the same keys. They don't have any write conflicts. So this is a way to get more throughput with this weaker guarantee. And to just drive this point home about the differences between some of these levels, let's just consider a small example. So say we are creating a banking application and we want to transfer some amount from a source to a destination account. Then a code snippet for this could look like this. So first we start the transaction, and then we read the source balance out of the source account. And then we have to check whether there's actually enough funds in this account. And if that is the case, we can go ahead and subtract the amount out of the source account. And then we can also update the destination account by reading its balance and then adding this amount. Now, if we didn't have logs or transactions or any other safe concurrency mechanism, then we can imagine all sort of nasty executions with this example. So for instance, it could be that two clients, they're trying to transfer money to the same account, but one of these transfers is lost. The money is not put into the destination, but yet it is still taken from the source. So a property we would like to have is that we have at most one transfer per account at a time. And actually, both these levels that I have presented to you, they give us this guarantee. So I think for serializability, it's quite clear that because transactions, they indeed run one at a time. So they cannot touch the same. Now, with snapshot isolation, then if we have two concurrent transactions, so two clients wanting to do something on the same account, then they are also rejected because they have no, because they have a right conflict if they touch the same account. So this is not allowed under that level. Okay, so then you might ask, I mean, what is the problem? We have these weak isolation levels, so let's just use those. So the problem is that there's no way for us to formally verify a database implementation using these weak levels. So it is indeed the case that there's a lot of literature about these levels. They often fall into one of these two categories. So they could be about these phenomena, which are concise examples of executions, just containing a handful of operations. And these are used to specify these weak isolation levels in the SQL standard. But if you look at one of these phenomena, then this is of course not general enough. We cannot look at this and then reason about all executions between clients and a database implementing one of these levels. On the other hand, we do have some very general models if we look in the database community. But the problem with those is that they work at such a high abstraction level. So they could be using graphs or state transition systems. So this is a graph in one of these models. So it's very hard to look at that and then reason about the individual instructions of a database. So to be precise, there exists no way to formally verify an executable database that runs weak isolation levels. And that's the problem we address in this work. And our tool of choice to solve this problem is separation logic. So as many others, we use the IRIS framework. And in the IRIS framework, usually when we prove a Hoare triple, that implies safety according to some operational semantics. And because IRIS is this framework, we can instantiate it with the semantics of our choice. So our instantiation is called an ARIS. And in an ARIS, we model the network. We model a UDP-based network where messages can be reordered, dropped, and duplicated. So we have tried to at least capture a quite realistic network model. Now, the cool thing about this is that we have a transpiler from a subset of OCaml, so we can write our database implementation in this subset. Then we can transpile it into our logic where it can be verified in IRIS and then mechanized in Rocq. So that's sort of our stack. So the contributions of this paper is first separation logic specifications for the most popular weak isolation levels. So these are read uncommitted, read committed, and snapshot isolation. So these are the ones, there are 4 of these levels in the SQL standard, and only 3 of them, these ones, apply to key value stores. So that's what we consider. Then we also have these formal proofs of implication inside the logic, where we show that actually snapshot isolation implies read committed, and read committed implies read uncommitted. And then the last and third contribution is this implementation and verification of a database implementation. So it's just a prototype. It's a very simple in-memory key value store. But it implements snapshot isolation, and then because we have these proofs of implication, then it actually also implements the 2 other levels. So in the rest of this talk, I'm just going to unfold these contributions and give you a better idea of how they actually work. So for the first bullet, how do we specify these isolation levels? I mean, what do they consist of? So there are 2 things that we have to do. first we have to come up with some resource definitions. These are of course not just any definitions. We have to, pick the ones that are going to work and really capture this level. And if you have used a bit of separation logic, you will see that often you have some sort of points to resource. And since we're using key value stores, these will often be, a key pointing to, for instance, an optional value or a list of values. So once you have found the resource definitions that you think are going to work, then you can go ahead and make some specifications for all these database operations. So start, read, write, and commit. So you end up with this bundle of specifications. And do notice that these are not using ordinary Hort triples. These are atomic Hort triples, meaning these operations expose a linearization point. So more technically than in Iris, we can use invariants to go from the precondition to the postcondition of these operations. And this is very important since we're in this highly concurrent setting with a lot of clients. So these clients are going to want to share resources through these invariants. So let me take you through how it works for snapshot isolation, this one level. So first, we have to come up with the resources. And we have two types of resources. We have like a points to resource for the global database state. So a key points to a list of values, and we call this list a history. So this is tracking all the values that has been written to this key in the past. So for instance, if it's 1, 2, 3, then in the beginning some transaction wrote 1, and then another one 2 and 3, and so on. We also have some points to resources for the local transaction state. So each transaction gets its own resources. So this is going to be a key pointing to an optional value. And then we have this subscript C, which is a connection. So transactions can be started on these connections with the database. And if we just recall a bit how snapshot isolation works, then each transaction has to read from this starting snapshot. So when we are creating these local transactional resources, they have to be created based on the global database state. And if we want the latest snapshot, then we have to take the most recent value out of these histories. So if the history was 1, 2, and 3, then this local resource is going to point to sum of 3. So let's see how this works around the start specification, which is responsible for creating these resources. So again, just to emphasize that starting is about creating starting snapshots. And as you see, there's a lot going on in this start specification, but let's just focus on how these resources are used. So in the precondition, we have the global database state. So this will often reside in an invariant such that many clients can actually create transactions concurrently. And so we provide this in the precondition, and then in the postcondition, you get back the unchanged database state, because starting a transaction doesn't change anything about the global state. And then based on this state, we create some local resources for the transaction which is just about to start. And these are created based on the latest snapshot, so we take the last value out of the history. So with these local resources, now the transaction is ready to do all the reads and writes it wants. And here we have to recall, so to specify read and write, let's recall how that transactions, they run sequentially internally. So you are reading your own writes, and in snapshot isolation for your non-local reads, then you're reading from this starting snapshot that we just created. So this implies that the read and write specifications can be specified just like a sequentially consistent heap. So something that we are quite familiar with. So as you see, the read specification, it immediately reads the value out of the pointer. And the write specification also immediately updates this pointer. We do have an additional resource, which is this key update status resource. and it tracks whether the current transaction actually wrote to this key. So we need this information to track these write conflicts at commit time. So if we just look at the commit specification, and again recall that commit time is all about checking these write conflicts, then I have just highlighted the part which is responsible for checking for these conflicts. So the specification takes a bunch of resources, some of which I have mentioned, and then it uses the pure facts from these resources to express this can commit predicate in red. So this can commit predicate could also have been named like, is there a write conflict? So if you are successful in committing, then this can commit predicate holds, meaning there is no conflict. And in the false case, it means it does not hold. There must be a write conflict with another transaction. So this was like the general idea of how it works for snapshot isolation, and we have also specified things for read committed and read uncommitted using this same methodology. And then we have proven these implications that I mentioned. So snapshot isolation implies read committed, and read committed implies read uncommitted. So I just want to remark about these implications, that it's not just implications between individual Hoare triples, it's actually these packages of resources and per operation specifications for all these operations. So in other words, it's these closed formulas on the form that exist some resources such that all the per operation specifications hold. So that is what we are doing these implications between. And having done these implications, we do gain some confidence that our specifications are correct, since if we look in the database literature, in these very detailed models, they specify the same levels and they're also able to prove the same implications. And in addition to this, to gain more confidence in our specifications, we have also verified a bunch of client examples, and these are based on these executions, these phenomena used in the SQL standard. Yes, so the last thing I just want to highlight is this database implementation. So that's like, I think this is the cool thing about our work, is that we have written an implementation, a prototype, in this subset of OCaml, transpiled it into our logic, and then actually verified it with regards to this specification. So the features it has, it's an in-memory key value store. It implements this original algorithm from 95, and it uses something called multi-version concurrency control with timestamps. So just to quickly tell you what that means, so we keep this timestamp counter internally, and then each transaction gets a start timestamp and a commit timestamp. And then if you look at the actual data, then for each key we have this ordered list of timestamp value pairs. So when a transaction wants to read, we take the starting timestamp, and then we just go down to this list and find the appropriate value. And when you want to commit, we can check for conflicts using the start timestamp again to see if something was written after you actually started. Yes, so just to summarize our contributions, we have these separation logic specifications for these three isolation levels. We have formal proofs of implications between them. And then we have a verified database implementation with regards to snapshot isolation, and because of the implications, then it also implements the other ones. So we also have an artifact with this paper where we have our database implemented in OCaml, and also all of our proofs in Iris and Rocq. Yeah, I think that was it.
Thank you for the great talk. Does snapshot isolation gives some sort of guarantee on commits, like at least one of commit succeeds, or is it always the case that you get false or true disjunctions?
So I didn't quite get the last part.
Oh, so like, so the specification for the commit says that you always get disjunction, and so either the commit succeeds or it fails. So I guess the spec itself cannot give you any guarantee on, like, some nodes some clients may eventually succeed or something like that.
No, you cannot get that. I mean, a client doesn't necessarily eventually succeed. That always depends on all the other concurrent transactions and what they are doing. But if you're only say your transaction is only reading something, then you can never have these conflicts. So then you know that you can always commit. So certain transactions, they actually know that they will commit. Yeah.
Thank you.
Hi, thanks for the talk. You said you cannot use the graph-based models to prove programs, but your colleagues have this Excel logic for weak concurrency, and they use the graph models directly. So I guess, why didn't you use it, and could you use it to kind of prove that your models are equivalent to the literature models?
Yeah, so I have actually made some work after I've done this, which does exactly what you mentioned. So we get that any sort of set of transactions that the database produces, from that you can actually prove that it's correct in these more abstract models and in the graph model, for instance. So this is a property we have, yes.
It's cool. Okay. So I guess it concludes your talk, so we should thank you again.